Tangent measures were introduced by David Preiss in order to prove what is now called Preiss's theorem. So our long-term goal over the next few weeks is to prove as much as we can of this theorem, in part because it's a very interesting theorem in and of itself, but also because it'll serve as motivation for our discussion of the various results and techniques concerning tangent measures. So what I'd like to do in this video is give an overview of the result and also an outline of our plan of attack over the next few weeks. Our objective over the next few weeks is to prove the following theorem. So suppose the m-dimensional densities of a radon measure mu exist almost everywhere. Then m must be an integer, and at almost every point x, there exists some constant cx and a plane vx, so that as we take the limit of this blow-up here, it converges weakly to cx times Hausdorff measure restricted to this plane vx. So recall from our discussion of tangent measures that a measure could have a very large, rich family of tangent measures at a given point. And in particular, the set of tangent measures could potentially be all non-zero radon measures. However, if the densities exist, then this result says that there is effectively only one tangent measure at each point, in the sense that all tangent measures must be multiples of Hausdorff measure restricted to some fixed plane. So this plane is effectively the tangent plane of the measure. Now, what's interesting about this result is that we started with a measure theoretic assumption that only told us about the asymptotic behavior of the mass of our measure in small balls. So namely, what this condition says is that for almost every x, if we look at the measure of mu bxr, as r goes to 0, this is asymptotically like some constant times r to the m. Okay, but from that measure theoretic assumption, we get some geometric and structural information, namely that as we zoom in at almost every point, the measure must be concentrating around some fixed plane. So we'll prove about half of this theorem over the next few weeks, and we'll learn some useful facts about tangent measures in the process. So each week we're going to cover a different aspect of the proof, and so we don't lose track of the plot. I'm going to outline what parts we're going to prove each week. So this week we're going to prove Marstrand's theorem, which says that if the m-dimensional densities exist, then m must be an integer. So notice here that in the above, I'm calling the above theorem Preiss's theorem as a convenience, even though it's the accumulation of a few different results by different people. Next week, we'll prove what Preiss's contribution to this result was. So Preiss showed that if the m-dimensional densities exist almost everywhere, then the tangent measures must all be flat measures. So they must all be multiples of Hausdorff measure restricted to m-dimensional planes. However, this doesn't finish the theorem because potentially the measure mu could have multiple flat tangent measures at a given point. Now, after next week, we'll begin our discussion of rectifiable sets and rectifiable measures. And in fact, Preiss's original theorem is a theorem about rectifiability of measures, but I'm stating it in an equivalent formulation above, so we don't have to discuss rectifiable sets yet. Now, when we do discuss rectifiability, we'll prove what's called Marstrand's rectifiability criterion, which says that if the m-dimensional densities exist and all the tangent measures of mu are flat at almost every point, then the above theorem holds that at almost every point there's actually a unique tangent measure that's just Hausdorff measure restricted to some plane.